The easiest pie with Mr. Carpenter. I am Mr. Carpenter, and today we are going to take an entire look at the second Algebra 2 review to help you better prepare yourself for this final. So, excuse my voice, I'm a tiny bit fatigued, but we press on. Let's start with the multiple choice. So Tasha deposits $1,000 into a bank account with a certain interest rate compounded monthly. The amount of money in the account after X days can be modeled by f of x equals 1,000 times 1.0016 to the 12x. So what would f of x look like if our interest rate was compounded annually? So right now is being compounded monthly because 12x means 12 times per month. So if I want this thing to measure annually, then I would need some way to represent this function where it only has an x in the exponent spot. That's the only thing I'm looking at. So you might remember a process in which we can go back in time and think about how this might have looked before. For example, it might have looked like this in the past. Okay. And this helps me because now this function has only an x in the exponent spot, and I can go in my calculator and find out what 1.0016 to the power of 12 is. So 1.0016 to the 12, that's 1.0193. So that would be C. So that would take that and it would convert it to an annual interest rate. Number 2, which expression is equivalent to x squared plus 5 over x squared plus 1? This is stowable. Everyone that's stowable will have a star. Okay, so make sure you understand your stowing principles. I'm not really going to go over them every single time. The idea here is I can turn this into an x squared plus 1 plus 4. Right, I'm taking that 5 and I'm turning it into a 1 plus 4. And then what that allows me to do is a very specific type of butterfly division where the x squared plus 1s divide out to 1, and then I'm just left with 4 over x squared plus 1. And that would be answer B. But I will show it to you one time so you can see it. Right? What does stow look like? We pick a number. I'm going to pick one with a decimal to be safe. Stow that into x. Then I'm going to type my original expression, x squared plus 5 over x squared plus 1. I'm going to get some number. And then I'm going to check out what I might think is, I got to remember what the actual answer was, 1 over 4. 1 plus 4 over x squared plus 1. They both return the same output, therefore they must be the same. I find that stowing a decimal number like 1.4, 5.2 will avoid any of the weird cases with this feature. So moving on to number 3, which function has a horizontal asymptote at y equals 4? So this is a review of what a horizontal asymptote might look like. The horizontal asymptote is a output that we can never reach, and it's going to look like a dotted horizontal line. So with one of these, so y equals 4, one of these, there's going to be some kind of invisible barrier that the function can just never really cross because of the restrictions of the function itself. So let's look at all 4 of these and see which one might satisfy this criteria. So the first one we have, let me get rid of this, is 4 to the power of x. And that one looks like it has a horizontal asymptote at 0, so that one doesn't really work. Let's try 4 to the x plus 4, which of course would just translate this to 4 units. And you can see here that that horizontal line, that barrier, seems to be right at y equals 4. So that would mean that the horizontal asymptote at y equals 4 is present here. And of course, you could we'll check out one of the other answers, log of x plus 4. So let's look at this one, log of x plus 4. Right, and there does not appear to be a horizontal asymptote because that graph is going to continue to increase further and further. So remember, especially with exponential functions, right? We can shrink, exponentials grow and shrink things. We can shrink something so much, but we can never make it a negative size. So these exponentials are always going to have some kind of horizontal asymptote. In this case, I'm going to pick B because that's the one specifically with a horizontal asymptote at y equals 4. Number 4, a solution to a radical equation. This one is solvable. You are able to test solutions for equations. We'll see what that looks like in a moment. But I'm going to make sure the root is by itself. And when it is, I'm going to square both sides. And in doing so, I get this. I'm going to FOIL a quadratic that I don't really need to show. So x squared minus 6x plus 9. I'm going to move everything over to one side so I can do a little algebra magic. So minus 2x to make it 8x, add 3 to both sides to make 12. And then you can do a quadratic formula or you can do a factoring. I'm going to factor this because the factors of 12 that add up to 8 would be negative 6 and negative 2, which means x equals 6 or x equals 2. So it appears to be B, but there could possibly be an imposter at play. So let's test each of these out. So 6 stowed into x, and then I'm just going to write this equation out, 2x minus 3 equals x minus 3. To type an equal sign, you're going to press second math, conduct a test. And if you get a 1, the equation is true. If you get a 0, the equation is false. So 1, that implies the equation is true. So let's try it out for 2, the other possible solution. That one output is 0. So 2 is an imposter, which means there is one solution, it is x equals 6. Okay. And if you're wondering how Stowe solves this for you, well, you can just go in and test out 6 and 2 and see if any of them are solutions, and you kind of get to ignore the backbreaking work. Number 5, if f of x equals 3 over x minus 2 and g of x equals x cubed minus 2x, or the solutions to the equation f of x equals g of x rounded to the nearest hundredth. Okay, this might look like something we've never done before, but believe it or not, we've done all of the ideas here. Now, obviously, hopefully you realize this is not something we're going to do algebraically. Okay, so the equation f of x equals g of x is simply saying, what if I took these two guys and set them equal to each other? So we're going to get 3 over x minus 2 equals x cubed minus 2x. Once again, we are not going to have the tools to solve this algebraically. That's going to be a huge chunk of our time. So let's think smarter about this, right? We could graph this guy, and we could graph that guy, and they are going to intersect somewhere. Right, we can find these intersection points, these values of x, and that's going to be our solutions. So let's go in and graph them. So 3 over x minus 2. 3 over x minus 2, and I believe the other one was x cubed minus 2x. I'm just going to double check. Yep, I'm going to graph them both. And you'll notice that there are 2 points of intersection. So I'm looking for those 2 x values. If I want to find that, I'll do a second trace. That allows me to find intersection points. And I'll just go close to here and enter, enter. So the first one, x equals 1.43. We'll do the other one. I've got to move the butterfly over to here. X equals negative 1.95. Those would be the values of x that would solve this equation. And that would be, no, not B. Whoopsies. That's y equals, I want x equals. So x equals 1.44 or x equals negative 1.95. That's how I solve that one. Number 6, which of the following is a factor of the function shown below? There are a lot of ways to go about this. So, of course, you could test each one out with synthetic division. So if I was to test out x minus 2, I would put 2 in the fortress, and then 4, 8, negative 10, negative 20, drop down, and, I would do my synthetic division. And if there was a remainder, then it did not divide nicely. It is not a factor of the function. If there's no remainder, it divided nicely, and that is a factor. You could also use the remainder theorem, which states that if x minus 2 is a factor of the function, then f of 2 would be equal to 0, right? A factor is a 0. And I'm going to show you that method. So I'm going to quit out of here. I'm going to stow 2 into x. And let's type in that function, 4x cubed plus 8x squared minus 10x minus 20, right? And if I plug in 2 and I get 0, then it would divide nicely and it is a factor. In this case, it is not, because I did not get 0. So let's try negative 4 for x plus 4. That is also not a 0. Okay, let's try negative 2 for x plus 2. That one is a 0 of the function. So x plus 2, it'll be a factor, right? And if you put negative 2 in the fortress to test this out and you divided it out, you should get a remainder of 0, I think. Number 7, this is stowable. I know a product means I'm going to multiply. So x plus 3 squared times 4x minus 2. That can go in to stow, and these all 4 products can go out into stow as well. I'm going to kind of quietly show you the algebra. It is as follows. We can rewrite that as repeated multiplication. Do a little FOIL or double distribute. So x squared plus 6x plus 9. That is being multiplied by 4x minus 2. And we can distribute this way as well. So let's do 4x squared times 4x, 4x cubed, x squared times negative 2, negative 2x squared. 6x times 4x is 24x squared. 6x times negative 2 is negative 12x. 9 times 4x is 36x. 9 times negative 2 is negative 18. So let's see. Looking like it's got to be B because these will combine to make a 22x squared. 36 minus 12 is 24x. And then there's a negative 18 in there. Okay. Number 8, if f of x equals root x minus 3, what would be its inverse function? So we have a tool for inverse functions. Our first thing is to rewrite f of x as y. So y equals root x. Then we switch x and y. And then we solve for y. So in this case, I would add 3 to both sides. So x plus 3 equals root y. And then the opposite of square root is the square. So in this case, y would be equal to x plus 3 squared, which would be letters. Number 9, the graph shows the radioactive decay of a substance over time. There's initially 8 grams of the substance, and after 8 days, there's now 0.8 grams. So what would the rate of decay of the substance be? Well, we know that y is equal to a times b to the x. That is our general exponential function, where a is the initial amount and b is the growth or decay factor. So we got to think about what we know here. We know the initial amount because we started with 8 grams of the substance. So I know I can put it in 8. I do not know the growth factor or the decay factor, so I'm going to leave that b. And then this other piece of information that I know, I can plug in to this and solve, right? I know for 8 days there was 0.8 grams. So I'm going to plug those in for x and y. That should be backwards. Let me fix that. Go. So after 8 days, there is 0.8 grams of the substance. We can divide both sides by 8. So b to the 8th power is 0.8 divided by 8 is 0.1. And then, right, if I'm getting rid of a square, I need a square root. If I'm getting rid of a cube, I need a cube root. If I'm getting rid of an eighth, I need an eighth root. So the eighth root of 0.1. So let's go in, math. I'm going to need that kind of root. I can plug in an 8. An eighth root of 0.1 is 0.749, which is going to be around 0.75. And a lot of people are going to jump the gun and say that it's got to be A because it's 75% decay, but you have to be careful. The growth or decay factor does not necessarily mean it's the rate of decay, right? So it's going to be 8 times 0.75, right? If I'm multiplying this by 0.75 every time, I'm actually losing 25%, right? It's 1 minus 0.1 minus the rate. So it's actually decaying at a rate of 25%. Okay. Number 10, which expression is equivalent to the cube root of x cubed y to the 4th to z? That is stowable. You are going to need to stow multiple things. So you can pick 1.2 and stow into x, 1.3 and stow it into y. If you want y, then you get alpha, text as the alphabet, and then just pick the one that has the y. And then 1.5 stow into z. So, I mean, it works just the same. You just have to pick more letters, but that's fine. Anyways, you learned in Algebra 1 that you can break up a root into its factors. We will do the same thing here. So the cube root of x times the cube root x cubed, cube root of y to the 4th, times the cube root of z. And the answer choices want fractional exponents, so let's see what happens. So if I have x to the a, and I'm taking the bth root of that, it would just be x to the a over b. So the exponent inside the root is the numerator, and the kind of root I'm taking is the denominator. So this would simplify to x to the 3 over 3, which is just x. This would be y to the 4 over 3, and this would be z to the 1 over 3, and that would be answer C. Number 11, if 4 times 5 to the 2x plus 1 equals 13, then the solution to the equation would be what? So we are going to work with our inverse operations, and we are eventually going to take a logarithm here. So let's see. Let's pretend for a moment that this was 4 times something plus 1 equals 13, right? Because I need the base of the exponent to be by itself before I do any nonsense. So I would subtract 1 and then divide by 4. And then that something would be equal to 3. Okay, same idea here. I'm getting that base of the exponent by itself. I'm going to subtract the 1. Divide by 4. And 5 to the 2x equals 3. Now that the base of the exponent is all by itself, I can take a logarithm. And we'll do a log base 5 of both sides. Because when the bases match the log, you can cross them out dog. So we're going to get 2x equals log base 5 of 3. And got to divide by 2 one more time to get log base 5 of 3 over 2. That is A. And there's a chance that the answer choices don't necessarily show the exact solution that you did. But that's okay because this log base 5 of 3 over 2, that's just a number. Right? So I can go in math alpha math, log base 3 of 2, log base 5 of 3 over 2. I can just find out the decimal, and I can plug in the other answer choices and see which one gives me the same decimal. So don't need to fret too hard about that. Come on. Close. There we go. Number 12, that's stowable. And actually number 11 was also stowable as well. Number 12 is expressed as equivalent. So 2 to the 4x times 8 to the x, we're looking for common bases here. So I want, 2 to the 4x, and then an 8, I can think of that as a 2 cubed to the x. So really it's a 2 to the 4x times a 2 to the 3x, and then we can, that's a product rule, keep the base at the exponents. 2 to the 7x. Let's see. Part 2, we are now finding the zeros of this function. However shall we do that? Well, we can factor this by grouping. So we can put this in a group, we can put that in a group, take out some greatest common factors. In this case, this would be 9x squared, and this would be x minus 2. And then over here, I can take out a negative 4, x minus 2. We notice these match, so we can do 9x squared minus 4 over x minus 2. This is all equal to 0 because I'm finding the zeros. If you want, you can factor that left-hand side even more, because that's DOPS, 3 squared, x squared minus 2 squared. Cover up the squares, you're going to see 3x minus 2, 3x plus 2. And remember, when I have factors being set to 0, well, that only happens if each one is equal to 0 itself. So we're going to get x minus 2 equals 0, so x is going to be 2. This one, I could solve it out. 3x plus 2 equals 0. 3x equals negative 2. X equals negative 2/3. And then this one's going to be x equals positive 2/3. And, of course, I can check on a graph to make sure that those zeros actually line up on the graph. Number 14, simplify this rational into the form c to the power of x, where x is a rational number. So let's start by, what we really want to do is a quotient rule. We want to divide the two, but we can't because one's in the form of a fractional exponent and the other one's inside of a cube root. So the cube root is what's really killing us. So on the top, we can do a product rule. C to the power of 3 over 4 plus 2. And on the denominator, we can do the same thing we did up here, where we're employing this idea. So this would be c to the power of 5 over 3. So 3 over 4 plus 2. If you don't know what that is, you can just 3 over 4 plus 2. It's 11 over 4. And then now the bases match. Nothing's inside of a root, so I can do the quotient rule. So I can subtract. So 11 over 4 minus 5 over 3. Oh, come on. You're a 3. 13 over 12. 13 over 12. And that is in the form c raised to the power of some rational number. So everything checks out. 15, finding the quotient of f(x) over g of x. Well, if we're going to divide two polynomials, we can do synthetic division. So x minus 2, 2 goes in the fortress. These guys go on the outside. Carry that down. Multiply, 4 times 2 is 8. Add 8 plus 3 is 11. Multiply, 2 times 11 is 22. Add 22 minus 1 is 21. These drop a power, so 4x plus 11, and then I have a remainder of 21 over x minus 2. That's it. 16. For a polynomial function, p of x, it is known that p of x has a degree of 3. It has 2 real zeros and 1 imaginary zero. And as x goes to infinity, p of x goes to negative infinity. And I just want to sketch a possible graph of p of x on the axis to the right. So we might have to draw this a couple of times to really get the idea. But let's start with the degree of 3. So the degree of 3 means that the largest exponent in the function is 3. So let's remind ourselves what a degree of 3 might look like. Right? That's x cubed minus 2x has a degree of 3. It kind of looks like that wormy shape that we've identified. So I know it's going to maybe possibly look like that. Right? But then it says it has 2 real zeros and 1 imaginary zero. So right now, it has 3 real zeros. So actually, that's I just noticed that should be 1 real zero and 2 imaginary zeros. So right now, the one that I have has 3 real zeros because it has 3 spots right across the x-axis. I can see it, I can visualize it. So I need to change it so it only has 1. So maybe it crosses once, but then doesn't really get down there a second time. And this would be degree of 3, 1 real zero, 2 imaginary zeros. Last thing, as x approaches infinity, p of x approaches negative infinity. So that means as the inputs go further to the right, the function should be traveling down towards negative infinity. Right now, my function is traveling up towards infinity. So we need to kind of take this and go the other way. So we can go down. There's my 1 real zero. Right, it's a degree of 3. As 1 real zero, 2 imaginary. And as the inputs go to the right, the function's going downwards. So this would be a possible function for p of x. 17. This looks like a lot of words. It is just an average rate of change problem. Logarithms are a great function to describe diminishing returns. When a person goes to the gym, there will be the most muscle growth over the first few sets, and this growth will diminish as a person does more and more sets, right? We know that's true. Otherwise, you can just go do 100 sets of bench press, and then you just be jacked in one day. But that's not what happens, right? You have to be smart with it. So we can use logarithms to describe the diminishing returns. So let's suppose that the logarithmic function log base 3 of x plus 3 describes the level of muscle activation, L of x, when x sets are done. So is the rate of change of muscle activation greater from set 1 to set 3 or from set 3 to set 6? Explain. So we're looking at an average rate of change. So we're going to need to do a slope calculation. If we're going to do a slope calculation, we need 2 coordinates. So let's look at this first one here, set 1 to set 3. So I did 1 set, what's my muscle activation? I did 3 sets, what's my muscle activation? We can look by just graphing it, right? So race, math, alpha math, log base 3 of x plus 3, and I can it looks like that. I can look at the table. So, set 1 to set 3. So on set 1, I'm getting activation of 3. Set 3, I'm getting an activation of 4. So we would do label our coordinates. Do a slope formula, 4 minus 3 over 3 minus 1, so 1 over 2 is my rate of change. Let's test from set 3 to set 6. So set 3, we know it's activation of 4, but what about set 6? Let's look. Set 6 is 4.6309. And we'll do another slope, 4.6309 minus 4 over 6 minus 3. And that would be 0.6309 over 3. That's 0.2103. So it would be greater from set 1 to set 3 because 1/2 is greater than 0.2103. So that would be set 1 to set 3 is more muscle activating. Number 18, simplify completely where I is the imaginary unit. So let's start, do just bits and pieces. So first we have 3x plus I squared. Okay, which is just it times itself. We'll double distribute. So through 9, silly Mr. Carpenter, 9x squared plus 3xi plus 3xi plus I squared. So 9x squared plus 6xi. I squared is equal to -1, so I can turn that to a -1. And then we have root -9 plus I to the 4th. Okay, so we'll root -9. I can put that in my calculator, assuming that I'm in A plus BI form, right? I'm allowed to type imaginary numbers. So root -9, that's just 3I. So 3I plus I to the 4th is equal to 1. And of course, if you forgot I to the 4th, you can type I to the 4th. It's 1. And you could have tested out I squared as well, and you would have gotten -1. Okay. So this is what we got. We got this guy minus this guy. We have to distribute a negative, so it's going to be 9x squared plus 6xi minus 1 minus 3i plus 1. These cancel, and this is the best we can do because there's no more like terms to combine. That's the best we can do. That's our final answer. Number 19. I'm going to spend a week in a cave searching for gold. The first day I'm going to find 12 ounces of gold, and every day afterwards, the amount of gold I'm going to find increases by 30%. So how much gold am I going to have after 4 days? So really, we need 4 numbers that we're going to have to add together. So day 1, day 2, day 3, day 1, I have 12 ounces. Okay. Day 2, I find 30% more gold. So 12 times, and if I'm going to increase by 30%, that's growth, so 1 plus the rate of growth, so 1 plus 0.3. Okay. So let's see, 12 times 1 plus 0.3, 15.6. That's how much I find. Day 3, I find 30% more of that, so it's just going to be 15.6 times 1.3. I'm going to find that much gold, 2028. And then on day 4, I'm going to find 30% more gold than that. So it's the same idea. In fact, 26.364. And then, so I found that much gold day 4, that much day 3, that much day 2, and this much day 1. So it's just a simple addition of all 4 of those. So this much, that much, plus that much, plus 12, and I have 74.244 ounces of gold. 5 lines. Last one, rational equation. Step 1, get common nominees. So we can factor that quadratic. It's going to end up being x plus 6, x minus 2. And if I want common nominees, well, this guy is going to need an x minus 2. And I'll do that on top and bottom. And this guy's going to need an x plus 6. And I'll do that on top and bottom. Once I have common nominees, I can cross off all denominators and solve for the numies. So we have 4 plus these guys multiplied together. So that'll be x squared. Let's see. Minus 2x. My brain. So x squared minus 2x minus 1x, so minus 3x plus 2 equals easiest distribution of your life. And let's move everything over, combine like terms. Subtract the 6, subtract the x. X squared minus 4x. Those cancel. So sometimes you're going to get a trinomial here, and you'll do the same factor trinomialing that you did to factor that guy. But sometimes you're going to get something that you can do a greatest common factor. Right? You can just factor out an x. This is for you, Jamel. You're in the video now. And then it's got 2 factors, x equals 0 or x equals 4. And then you just got to check for imposters. I'm going to cut the video there.